these are a couple of ways that we have to represent the sharing of electrons, the formation of covalent bonds. And the examples all in this slide are all what we call homonuclear molecules. It means that they're made of one type of atom, as opposed to heteronuclear, which means when we have more than one type of atom in the molecule. So instead of writing the two dots in the middle of the two hydrogen atoms, we write a line. In the case of chlorine, again, those two electrons being shared, we can write them as, a line. And in the case of nitrogen, the way that nitrogen makes bonds means that when you have two atoms of nitrogen joined together, there are 6 electrons being shared in three different covalent bonds. So molecules, atoms, sometimes they will share 1 pair of electrons, sometimes 2, and sometimes 3. And again, it's beyond the scope of this module exactly when they share 1, 2, or 3. In general, is because it meets its electronic needs. It makes them achieve a more stable state and more complete electronic configuration. So we've got here the molecule of nitrogen, N2, which is 3 covalent bonds joining those 2 nitrogen atoms. So this way of representing the molecule tells us how many bonds we have in between 2 atoms, or in the different bondings of a molecule. We have 1, 2, or 3. So for example, if I draw the molecule of water, which is H2O, the molecule of water is an atom of oxygen attached to 2 hydrogen atoms. And I've drawn them in this V shape. And you might wonder, why am I drawing them in that V shape? If I write, for example, a molecule of CO2, carbon dioxide, in this case you have the carbon in the middle, and it has 2 covalent bonds to each of those 2 oxygen atoms. So the carbon is in the middle and the 2 oxygens are on the sides, and there are 2 covalent bonds between those carbon oxygens. So why do I draw them like this? Why have I decided to draw the molecule of CO2 as a line, as a linear molecule, but the molecule of water I've done this V shape? And that's an interesting question. And that is because those lines are not the only electrons that are among that central atom. To understand the structure of a molecule, whether it will be, all the atoms will be in a line, it will be a V shape, it will be a square, it will be a triangle, whatever, we need to understand a little bit about how many electrons are around that central atom. And there is a model called the valence shell electron pair model, valence shell electron repulsion pair model. And it's based on the idea that when you have all these electron pairs around a central atom, those electron pairs will repel each other. So then they will try to establish themselves in a 3D structure, so they are as far as possible from each other. So when I draw the molecule of water, H2O, the reason why I draw it in as a V-shape structure is because there are 2 electron pairs around this oxygen, which are, you don't really see them. I mean, you see them if you do, if you study in X-ray diffraction, the structure of the molecule of water, but we don't draw those electrons that are there. They are sitting on the oxygen. They are electron pairs that belong to the oxygen. They are not shared with the hydrogens at all, but they are there occupying a space. And that's what means that the 2 hydrogen atoms are not against each other. They're making a V shape. The reason why the molecule of carbon dioxide is linear is because there's nothing around that atom of carbon. There are no additional electron pairs, so there's nothing preventing the oxygens to be as far away from each other as possible, those electron pairs to be as far as away from each other. Boron trifluoride, as we call trigonal planar. It's the boron is in the middle, and there are 3 fluorine atoms pointing towards the corners of a triangle. And the reason again is because there are no electrons or extra electrons around that boron that can be used to form, there are internal electrons, those are always there. But in terms of making additional bonds, there are no electrons there that are occupying a space that you need to account for. And the reason that methane is tetrahedral is because again, around that carbon, those 4 lines that you see going through the 4 hydrogens are the electron pairs in the outer shell. And the different bonds that it's making with the 4 hydrogens. There aren't any additional electrons in that outer shell that are occupying any space. And it is beyond the scope of this module to see why we don't know that. If you have ever done electron configurations, you will know why those electrons are there. It doesn't matter. The reason I'm introducing this is because when I draw the molecule of water and I draw it like this, I want you to remember that there are electrons around this oxygen that are not being used by bond to make bond with the hydrogens, but they are there. When I draw the molecule of ammonia, NH3, I'm going to draw it like this, and that is because there are 2 electrons. There is an electron pair in the outer shell of that nitrogen that is not being used for the bond with the hydrogens, but it is there. It's occupying a space, and it needs, it's present in the molecule, even if it's not intervening in the bond.